All right, now we move on to investigation 5B. So in 5A, we talked a lot about warm air masses, cold air masses, fronts moving through, and how that all affects air pressure horizontally. Now we're going to talk about how warm and cold air masses affect air pressure vertically. Before I begin, if you are taking this class at the same time as my online or on-campus class, sometime around this time, you're going to hear about something called the two-column model of air pressure. And this literally is just that. So if you have already heard that in my lecture class, you are good. You're gonna fly through this. If you hear this first, you're gonna fly through that later. So, and if you haven't heard it yet in my lecture class or anybody else's lecture class, don't stress. You're perfectly fine. I'm going to talk about how this works here. There's also a good little video that the AMS itself does that I'm going to link in the comments. And let's jump in. So, the goals for this lab are first to identify how air density and temperature affect pressure levels, and then to compare the upper atmosphere of a warmer location to that of a cooler location. And usually the way I do it in my lecture classes is I usually talk about it in terms of columns of air. But this, in this particular course and in this particular investigation, we're actually going to get to play with blocks. And here's how these blocks work. So right now you see a red block and a blue block. And just so you know, us in the wonderful world of weather, we love to indicate warmer air with a red block and cooler air with a blue block. And that's essentially what's going on here. So here's what you need to know. Both of these blocks have the exact same weight. As a result, since we know that pressure is the weight of the air above us, we would know that each of these blocks is exerting the same pressure on the surface. And in this case, we're talking about, actually let me get my little laser pointer here. In this case, we're talking about this table. So right now, in these two stacks, this red stack and this blue stack, at the surface, at this table, we are experiencing the same pressure in either stack. And when I talk about the two-column model, I say, okay, same surface pressure. But what about if you travel up in elevation? Like, let's say we actually had a second surface here. How would the pressure be different in each of these stacks? Well, we'd still have some red above us, so pressure would be higher over here than it would be over here. And that's essentially what happens. That's essentially what happens when you have a warmer atmosphere. It's going to be taller than a cooler atmosphere, which is going to be a lot shorter. And in fact, I'm also going to put in the comments, as I'm writing this video, there's a major cold outbreak happening on the East Coast of the United States, and I was taking a look at Buffalo, New York last night, and there was an instance where the top of the troposphere, the tropopause, was way lower than it normally is. And that's because when you have cooler air, that causes the atmosphere to shrink in size. It becomes a lot shorter than it would otherwise be. And same thing happens here. So red block, warmer air, taller. Blue block, colder air, shorter. But again, they both have the same weight. As a result, at the surface, they exert the same pressure. Now let's actually complex this a little bit, and this is basically what I was just talking about. Let's say, again, if you're at the surface here, both of these stacks have the same pressure. And how can you identify the pressure at the surface of this table? Count the number of blocks above you. In the red stack, you have 1, 2, 3, 4, 5 blocks above you. So we're just going to say that the table is exerting, or has a pressure exerted on it of 5 blocks. Meanwhile, in the blue column, you also have 1, 2, 3, 4, 5. So down here at the surface on this table, both columns still are exerting the same amount of pressure. But now let's travel up in the atmosphere. Let's actually travel up to these two imaginary surfaces, surface 1 and surface 2. And again, I don't want to give away answers here, partially because I want you to do it, and partially because I don't want the AMS to sue me. And I love the American Meteorological Society, so I want to be on their good side. But I will give you some hints right now. So here at surface 1, if you wanted to determine the pressure above surface 1 that's being exerted on surface 1, again, simply count the number of blocks. And you're going to get a ratio. So you're going to have X number of blocks in the blue stack divided by Y number of blocks in the red stack. And so you'd then say, okay, well, the blue stack has X over Y, the pressure. Or the red stack has Y over X, the pressure. Basically, the idea here is that as you're traveling up in the atmosphere, the pressure differences become greater between these two stacks. And again, the reason why is because the red stack is taller, the blue stack is shorter. And then if you went up here to pressure level 2 or to surface number 2, that difference becomes even greater. Down here, the difference was one thing, but if you actually went up, it ended up actually being even larger. And again, I'm not going to give the answers away, but just know that as you're going up in height, the difference between the two stacks, the difference between the pressure exerted at that surface becomes greater. And this is actually true in the two-column model as well. And this is basically the next diagram that they drew there. And basically what they wanted you to do is they wanted you to connect the top of the tall stack to the top of the short stack and create these lines basically indicating what are called pressure surfaces. So this is the height at which the pressure is the same in each of these two stacks. And if you notice that as you travel from the tall stack to the shorter stack, that height becomes shorter and shorter. This pressure level slopes downward. Now, how does this actually apply to the atmosphere? Well, in the atmosphere, when you have warmer air, pressure levels are typically higher. And then as you travel, let's say you're on a flight, and let's say you start here, like let's say maybe this is, I'll use my hometown, Long Beach, California, and let's say this is Anchorage, Alaska. If you're traveling along the same pressure level, what actually is happening is you're actually decreasing in elevation. You see, when I say pressure level, I'm talking about right here at this height, the pressure is 1, 2, 3, 4. Over here, the pressure is 1, 2, 3, 4. So this line connects those two, here where the pressure level is 4, and then down here where the pressure level is 4. So again, the idea is that as I'm traveling from the warmer air to the cooler air, that pressure level is sloping downward. That pressure level is sloping downward. On the other hand, if instead of traveling at a constant pressure level, I instead travel at a constant altitude, what that's actually going to do is that's going to cause air pressure outside to change. In this case, if I start in a warm city and fly to a cold city, what's actually going to happen is even if I maintain the same actual altitude, my pressure outside is going to decline. So, for example, let's say I'm at this given altitude right here. And I start here in the center of the red stack, and currently I have 1, 2, 3 blocks above me, so my air pressure is 3. But then I jump on my Boeing 747 and fly over to the center of the short stack at the same elevation. So now I'm staying at the same elevation, but now instead of having 3 blocks above me, I only have 1. So instead of having 3 blocks above me, I only have 1. So my actual air pressure is declining as I'm traveling from the warm air to the cold air. And then the opposite is true too. If I start in the cold air, let's say I board my plane here in the cold city, and then I fly up to this constant altitude, and travel to the warm city. As I'm traveling along that same elevation, my air pressure is going to increase in this case. Because I'm traveling from this location where I only had 1 block above me to this location where I now have 3 blocks above me. And so this may take a few minutes of getting used to. I definitely recommend checking out that video that I'll post in the comments and also on the Canvas assignment that's done by the AMS. I want them to kind of actually show the blocks and everything. But now, how does this actually relate to the atmosphere? So it's fun to play with blocks and talk about warm air, cold air, and all that kind of stuff. Well, the way that it actually works in the atmosphere is if we were to compare 2 locations. So let's say the states of Florida and New York. At the surface, so now think about down at the bottom of the table. At the surface, both locations may very well have the same air pressure. However, because Florida is a warmer atmosphere, those pressure levels are going to be higher as you go up. Air pressure is not going to decline as much as you go up. And so each of these pressure levels, 925, 850, 700, 500, and so on, are actually going to, they're actually going to be higher. On the other hand, in New York, the pressure declines a little bit faster with height, so the pressure levels are going to be a little bit lower. And I'm going to have you actually print out or copy this to a Paint document or whatever document you're comfortable with scribbling all over. But I will do the first one for you. And I'll actually start here at the top. So let's see. Okay, so basically what they want you to do is connect the 2 arrows of same pressure. So here, connect the 150 millibar arrow at Florida to the one at New York. That looks more like a curve. You could use a straight edge if you want to. In fact, I'm going to erase this and let's see here. And it's somewhat better. There we go. Yeah, if you print this out on a sheet of paper, use like a ruler or the side of a book or even the side of another sheet of paper, some kind of straight edge. But it still kind of shows you the same thing, actually. If you travel from Florida to New York, you're actually sloping downward. If you travel from New York to Florida, you're sloping upward. And what's happening is if you stay on that constant pressure level, traveling from New York to Florida, your actual altitude is increasing. On the other hand, if you're traveling from Florida to New York, your actual altitude is decreasing. Now, if you were to, let's say, travel at a given elevation, so let's say here at 12,000 meters. If I were to fly from Florida to New York, what actually would happen is over Florida, my air pressure is actually higher than 200 millibars, so I'm actually below the 200 millibar surface. As I fly to New York, at some point my pressure drops to 200 and then ends up being below 200, so I'm now above the 200 millibar surface over New York. So as I'm traveling at a constant elevation, again going from the warm air mass to the cold air mass, that results in a decline in pressure outside. Now the last thing I'm going to talk about, and I'm going to do you the favor of, there are 2 Stuve diagrams that you kind of have to flip back and forth from, and so I'm going to take a moment later and actually do that. But for right now, a common question that I get on this particular lab is they're going to compare 2 cities and they're going to say higher and more moisture, lower and more moisture, or whatever. And people usually understand that, you can determine higher temperature versus lower temperature. But a lot of people get confused about moisture content. And in order to find out the moisture content, you simply look at the dew point. And so, for example, let's say Denver's dew point is 75 and Little Rock's is 70. In this case, Denver would have a higher dew point than Little Rock. in that particular case, Denver would have a higher dew point than Little Rock. So when you actually are asked this question in the lab manual, do that comparison. Compare the dew point at Little Rock to the dew point at Denver to determine which one has more water vapor. The one with the higher dew point has more water vapor. Okay, finally, you're actually given these two STUV diagrams. This one's for Denver, this one's for Little Rock. And they want you to make some comparisons of the two. Now, the first thing I'll mention is that Denver, often referred to as the Mile High City, is actually at a much higher elevation. It's at an elevation of around 5,200, 5,300 feet, depending on what part of the city you're in. But they refer to it as the Mile High City. And one of the things that you'll notice if you look at a STUV diagram, there's nothing down here near the surface. So there's nothing down here near 900, 1,000. And in fact, you really don't see anything until just a little above 850 millibars. And that's just because all of this down here isn't Denver's not there. Like that's below the altitude, the elevation that Denver has. So this is actually the surface for Denver right here. And so you don't get data from down here. Now with that said, that's good to keep in mind because as you compare Denver to Little Rock, what you're actually going to want to do, and this is what I recommend doing. Let me get my little highlighter here, or my little laser pointer. What I recommend doing is that they give you two arbitrary heights, they say between X height and Y height, or between X pressure level and Y pressure level. Little Rock was generally warmer or colder than Denver. Well, to figure that out, what I recommend doing is finding somewhere in that range. I know 450 is somewhere on that range, so I'm just going to hover my little laser pointer over it. If you want to, you can actually just put your finger right there right now. And because I don't want to give away the answer, I'm going to now hide my laser pointer. But if you toggle between there and Little Rock, look at how the line has changed relative to your finger. That black line to the right, that's the temperature line. The one to the left is dew point. We're not worried about that right now. But the black line to the right, that's dew point, or that's air temperature. The black line to the right. If that black line has moved further right, that means that the temperature is warmer. If the black line has moved further to the left, that means that the air temperature is cooler. So here's what I mean, not to give away answers. I'm actually going to look up here at 150 millibars. This is actually outside of the range. And if you take a look, Denver's temperature at 150 millibars is right around negative 55 degrees Celsius. Little Rock's temperature is around negative 65 degrees Celsius in that case. So at that portion of the atmosphere, Little Rock is actually cooler than Denver at that given height. But again, that's out of the range. You just want to do the same thing, but at a more arbitrary height like 400, 450 or so. And that's practically it for this lab activity, and actually for this module if you're taking my online lab class right now. And as always, if you have questions, comments, concerns, anything to let me know about, please don't hesitate to reach out to me. I would say this is actually one of the more complicated labs of the course. Not as much as the first lab, but still, if you have any problems, just let me know. I'm here to help. All right, good luck on this lab, and I hope you do well.